We present an algorithmic framework for creating readable tree layouts. Even though the tree layout problem is an old, well-known, and some would say solved problem, we define the readable tree layout problem and show that there is more work to be done in this domain. Such layouts can be used to drive visualization systems for large graphs, as shown in this short video. What is a readable tree layout then? Well, most real-world graphs have labeled nodes and edges that capture similarity or dissimilarity values, rather than just connectivity. For example, one of the graphs we work with is the Google Research Topics graph. Nodes are research topics, and edges connect similar topics. Looking at a plain node-link representation of this graph without the labels, and ignoring the similarity between pairs of topics, can give us a general idea of its global structure, but it misses key insights, such as which research topics are closely related, what groups of topics there are, and so on. We define two hard constraints and two properties that should be optimized for readable tree layouts. The first requirement is that node labels should be readable and should not overlap. As seen in this image, it is impossible to read many of the labels on the left, due to the overlapping nodes. On the other hand, our algorithmic framework produces a layout shown on the right, which is more readable as none of the words overlap. The second requirement is that layouts should have no edge crossings. As shown in the literature, edge crossings reduce readability of graphs and can be completely avoided in trees. Determining path length is harder in the example on the left than in the output from our algorithm on the right. The first property to optimize is desired edge lengths. In many real-world datasets, edge lengths are meaningful. For example, in the tree of life, the length of an edge corresponds to the evolutionary time separating two species. Even in unweighted graphs, the desired edge length should be uniform, as significant edge length deviations can create false impressions of clusters where there are none. The second property to optimize is compactness. If we ignore compactness, we could take any crossing-free drawing and scale it down until the labels no longer overlap. However, this leaves us with a lot of wasted white space in our drawing and requires a lot of zooming to read any labels. In the example here, the right shows the output from one of our methods, while the image on the left is obtained from another algorithm that ignores compactness. Our compact layout allows us to see more of the underlying data without needing to zoom out, which would make the labels more difficult to read. In addition to the two hard constraints, no overlaps and no crossings, and the two soft constraints, edge lengths and compactness, we also care about scalability. With this in mind, we develop a parallel version of our algorithm. Not all graphs and trees are small, and practical tree layout algorithms should be able to handle large inputs. We show that the parallel algorithms can handle inputs with hundreds of thousands of nodes in seconds. For this parallel algorithm, we use OpenMP. To summarize, we have two hard constraints, no label overlaps and no edge crossings, and two optimization goals, realizing desired edge lengths and compactness, while also providing scalability via parallelization. With these motivations, we note that several of them can lead to contradictory results. For example, suppose we have a graph where a single node is connected to many others with the same desired edge length. If we keep the edge lengths, this will lead to a layout that is not compact. If we put all of the nodes together in a very compact way, this will lead to not all of the edges achieving their desired lengths. For this reason, we give two variations of our algorithm, one that prioritizes desired edge lengths and one that prioritizes compactness. Here is an overview of our algorithms. We have the readable tree layout RT, which needs just a single processor, and the parallel readable tree layout PRT, which can draw large graphs with hundreds of thousands of nodes using multiple processors. Each of these algorithms has two options, one focusing on edge lengths L and the other focusing on compactness C. Note that these two optimization goals, edge length realization and compactness, are incompatible, which motivates the two variants. Our readable tree layout algorithm follows these basic steps: initial layout, iterative improvements, and a final output check. They differ on how these steps are performed and what layout aspect they optimize. Before we can get to the layout algorithm, we need to spend some time pre-processing the data to create a multi-layer representation of the input graph. Many graphs already come with node weights and edge weights, but if the graph is unweighted, we assign weights based on standard measures. A multi-level Steiner tree algorithm extracts a suitable hierarchy of trees, with the input graph on the deepest level and progressively smaller representations on the levels above. This hierarchy is needed in the final map visualization for semantic zooming, while the layout algorithm computes positions for every node in the graph, the deepest tree. Desired edge lengths are also required. These can be given by the edge weights, if only the layout algorithm is used, or by the level of tree that the edge first appears on, if the map-like visualization is used. To help the options with desired edge length and compactness, we provide two initial layout algorithms. The desired edge length keeps the edge lengths exactly, but does this at the expense of compactness. And the compactness one keeps the layout relatively compact, but does not take the desired edge lengths into consideration. Both of these algorithms ensure that we have no edge crossings in the initial step. Given an initial layout optimizing edge lengths or compactness, a force-directed algorithm is employed to improve the soft constraints while maintaining the hard ones. The forces involved are a force to preserve edge lengths, a force to remove overlaps, a distribution force, which is a node-node force to keep the nodes from getting too close or far, and a node-edge force that tries to keep the labels from overlapping the edges. We ensure that no edge crossings are introduced by not performing any move that would create a crossing. Here is a comparison of our layouts. In the box, we have our algorithms RTL, RTC, PRTL, and PRTC, compared with two already existing algorithms. CIR is a circular layout algorithm from the Y file system, and SFDP plus Prism is the scalable force-directed algorithm from the GraphViz library, followed by an overlap removal phase. Algorithms such as CIR produce no edge crossings, but distort edge lengths and might suggest a graph structure that is not necessarily there. SFDP plus Prism produces compact layouts that represent the underlying structure well, but they have many edge crossings. We provide a more careful analysis next. We have three evaluation criteria: desired edge length realization, compactness, and runtime. Here I will briefly discuss the qualitative evaluation of the edge lengths. In the image below, we see the same graph laid out by the RTL and RTC algorithms. Edges in these layouts are darker if the length of that edge is far from the desired edge length, redder if compressed, bluer if stretched. The RTC algorithm has a worse average edge length deviation, while the RTL does its job with very low edge length deviation. Here we can see a closer view of the graph. Note that the RTC algorithm has smaller errors that affect most of the edges, while the RTL algorithm has only a few edges that do not match up well. This table gives the numeric values of the differences in edge lengths. The best score for each graph is bolded. As expected, RTL, our edge length algorithm, performs better on the edge lengths up until it cannot draw the graphs anymore. At this point, our parallel algorithm, PRTL, and SFDP and Prism are comparable. Although, as we will note many times, SFDP plus Prism includes edge crossings. Next, we will look at compactness. While these two visualizations may look like they take the same space, the CIR drawing has been scaled by a factor of about 40,000 to fit on the same scale. This means that to read the nodes on CIR, we have to scale down a lot, and we'll end up with mostly white space. For comparison, our algorithm gives the same number of nodes in a much more compact space. This table gives the numeric values for the compactness measurement. This is given by taking the sum of the areas of all the labels and dividing it by the total area used in the layout, resulting in a value between 0 and 1, with higher scores corresponding to better area utilization. The best score for each graph is bold. This figure shows that on most of the input graphs, our compactness algorithm, RTC, or its parallel version, PRTC, outperforms the others. Again, SFDP plus Prism produces compact layouts, but they have many edge crossings. Here we have graphs which show how the PRT algorithm scales with respect to the number of cores and the number of edges. Note that in terms of the number of nodes, the PRT algorithm scales linearly. This allows for drawing much larger graphs than the RTL or RTC algorithm. This is the runtime of each of these algorithms. Our parallel algorithm, PRT, outperforms all, except for SFDP plus Prism, which, once again, produces edge crossings. Now we will show a quick demo of our visualization system. Note that in the beginning we have set up a hierarchy of trees. Then, as we scroll down into the graph, we can see more and more nodes come into view as we reach deeper levels of the tree. We use GMap as a base for the clustering and country metaphors. You can see here that our labels do not overlap throughout our scrolling, and there are no edge crossings anywhere. Edge lengths are based on the level that their source and target first show up in. Now we will discuss the limitations of the work here. First, we believe that crossing-free, overlap-free layouts are important for readability, but this remains to be validated with human subject studies. Next, we only compare against 2 prior algorithms. This is because we could not find more than 2 that did even some of our requirements, and no algorithms tried to do them all. Next, we know that force-directed algorithms give a large parameter space to explore. While we found good parameters for our problems, much of this parameter space remains unexplored. Finally, many overlap removal tools exist. It would be interesting to see them be modified to keep the topology of the graph. For example, maintain no edge crossings while removing the label overlaps. If you would like to learn more, the link is there. On that page, you can see more examples with a map-like visualization of these layouts. Also on that site are links to the paper and the code.